Imagine this scenario. It's like a Tuesday morning, you're sitting at your desk, sipping your coffee, and you finally hear the delivery truck pull up.
Oh, the absolute best feeling.
Right, you've been waiting for this for weeks. It's the brand new, ultra-premium packaging you designed for your agency's biggest client.
Like a massive product launch, right?
Exactly, a huge deal. So you go downstairs, you slice open the first corrugated shipping carton, and you pull out one of the 10,000 pristine matte finished boxes.
Beautiful.
It looks gorgeous. I mean, the colors are popping, the foil stamp is catching the light exactly the way you envisioned it on your screen. And then you go to fold the top flap closed.
And it catches.
It catches. It doesn't lay flat. There's a tiny, almost imperceptible buckle in the cardboard right at the hinge.
Oh no, I can feel the anxiety already.
Yeah, you try to force it and the paper cracks. The sleek luxury experience is instantly ruined. So you sweat through your shirt, grab a physical ruler, and you realize the die cut line is off by a fraction of a millimeter. Just a hair.
But multiplied across 10,000 units.
Exactly. That tiny fraction just turned a $50,000 print run into a mountain of highly expensive, useless garbage.
It is the ultimate nightmare for anyone in this industry. And, the most frustrating part is that it is entirely preventable. It almost always comes down to a fundamental misunderstanding of the physical math.
Exactly. And that is why we are here today. So welcome to the show. If you are a curious learner, someone who is just starting to navigate the early days of your design career, you are absolutely in the right place.
Because today is all about prevention, right?
100%. Today, we are entirely focused on preventing that $50,000 mistake. We are taking a deep dive into the mathematical language that separates the people who just, push pixels around on a screen hoping things work out from the actual professionals who architect foolproof visual systems.
Yeah, it's that transition from digital theory to physical reality. It's where you realize your weightless, undoable digital file has to survive in a very rigid, very unforgiving physical world.
To make sure you survive that transition, we are pulling our insights today from a very specific, incredibly vital source. We are breaking down Chapter 1, Measurement Conversion Charts from the Graphic Design Reference plus Specification book.
Which I know sounds a bit dry.
Right, I know what you might be thinking. A chapter on conversion charts sounds like the driest, most agonizing reading imaginable. If you just flip to the section, it literally looks like a tax document from the 1800s.
Yeah, rows and columns of microscopic decimals, fractions, and archaic-sounding units.
It definitely doesn't scream creative inspiration, that's for sure.
No, not at all.
But I promise you, by the end of this deep dive, you are going to see these numbers as your absolute greatest superpower. We're going to translate this raw data into the real-world scenarios where it actually dictates success or failure.
It's the secret language of the pros.
It really is. But before we get into the weeds, I have to insist on something. This cannot just be a theoretical conversation for you. You literally cannot guess these tolerances in your day-to-day work. You need this specific toolkit physically sitting on your desk.
Yeah, it really is the ultimate safety net. I mean, I keep mine open constantly when setting up print files.
So do yourself a favor. If you are listening to this at your computer right now, pause us. Go down to the description of this deep dive. You will see an Amazon link https://amzn.4bybob- and a QR code.
Just scan it with your phone.
Exactly. Scan that code, use the link, and buy the Graphic Design Reference plus Specification book. You are going to need it to follow along with your career. And while you are down there in the description, hit follow on this show. We're going to be doing a lot more technical design breakdowns and career building content, and you really don't want to miss the tools that actually build your professional foundation.
Because you want to be the person the production team trusts, right?
Right.
The designer whose files actually work. That starts with the material we're covering today.
Okay, let's unpack this. I want to start our journey at the absolute microscopic level. Before that disastrous box was ever printed, it started as a blank white artboard in a software program.
Right.
And before you can draw a single shape or set a single line of type on that artboard, you have to define the units you are working in. For a lot of people, especially those doing web or UI design, they default to pixels.
Which makes sense for screens.
Yeah, absolutely.
Okay.
But for professional layout, typography, and print, our source dictates a very specific holy trinity of measurement, picas, points, and millimeters.
It's a completely different paradigm, moving from the blunt instrument of the pixel to the surgical precision of the point.
Surgical is exactly the right word. The factual breakdown the source provides here is just staggering in its specificity. Let me walk through the core equations the book lays out. It starts relatively simply. 1 pica is equal to exactly 12 points.
Okay, a nice clean ratio.
Right. But then we cross into the imperial system, and it states that 1 pica is 0.166 of an inch. And in the metric system, 1 pica is 4.2175 millimeters.
Which means the point, that fundamental building block, is incredibly tiny.
Incredibly tiny. The source states that one single point is 0.0138 of an inch. It is 0.0835 of a pica, and it is 0.3515 of a millimeter.
Wow.
Yeah. And when you zoom out to a standard inch, the text specifies that 1 inch contains exactly 72.27 points, which equals 6.0225 picas.
72.27 points to an inch. That number has governed publishing for centuries.
And this is exactly where I want to push back, because I think a lot of designers entering the field today look at these numbers and feel completely alienated. I mean, I look at 1 point equaling 0.0138 of an inch, and my brain just rejects it.
It's hard to visualize.
Exactly. Like, a human hair is roughly 0.003 to 0.04 inches thick. So we are talking about a unit of measurement that is literally 3 or 4 human hairs wide.
Right.
Why on earth are we forcing early career designers to memorize a system this microscopic and seemingly random? Why not just say, hey, we live in a modern world, just use millimeters for everything. Millimeters are base 10, they're logical, 10 millimeters in a centimeter, easy math. Why hold on to the pica and the point like it's a sacred religion?
That is the exact trap a lot of modern designers fall into. The assumption that because base 10 is easy to count on your fingers, it's the best system for dividing visual space.
I mean, it seems like common sense.
It does. But what's fascinating here is that the perceived arbitrariness of the point system, that base 12 logic, is precisely what makes it mathematically superior for typography and grid systems.
Mathematically superior how? Because if I try to divide something by 12 instead of 10, I usually need a calculator.
Think about what you are actually doing when you design a layout. You are taking a fixed canvas, a page, a poster, a screen, and you are dividing it into proportional columns and gutters so that human eyes can comfortably track the text.
Okay, sure.
It's an exercise in fractional division. Now, let's try to divide a space using your logical base 10 millimeters. Say you have a column that is exactly 10 millimeters wide, and you want to split it perfectly into 3 smaller columns for a complex data table.
Okay, 10 divided by 3. That's
Wow.
3.333. Infinitely repeating.
Exactly, you hit a repeating decimal. In the physical printing world, you cannot print an infinitely repeating decimal. Eventually, the software, or the machine, has to arbitrarily round that number off.
Like down to 3.33.
Right. And over the span of a large document, those tiny rounding errors accumulate. And suddenly your grid doesn't align perfectly. Your text looks jittery. Now let's look at the logic of the pica. 1 pica is 12 points. The number 12 is mathematically beautiful for a designer because it is cleanly divisible by 2, 3, 4, and 6.
Oh, I see. So if I have a space that is 1 pico wide and I divide it into thirds, it's exactly 4 points, no decimals, no rounding errors.
Perfectly clean whole numbers. You can divide that space in half, which is 6 points, into thirds, 4 points, into quarters, 3 points, or into sixths, 2 points.
Wow. Okay. That is super clean.
It is. That hypergranularity gives you an unbreakable baseline grid. When a professional designer is laying out a 400-page textbook, they set up a baseline grid. It's an invisible set of horizontal lines that run across every single page. Every line of text, whether it's a giant headline or a tiny footnote, must sit perfectly on one of those lines.
And if you use millimeters, the math breaks down.
It completely shatters. Let's look at the conversion from the source again. 1 millimeter is 2.845 3 points. If you try to adjust the vertical spacing between your lines of text, which we call leading by a single millimeter, you are jumping nearly 3 points at a time.
Which is a huge jump for text.
Huge. To the human eye, a 3-point jump in line spacing is massive. It can completely change the tone and readability of a paragraph. It makes tight, dense text suddenly look airy and disconnected.
Wait, let me make sure I'm tracking this. So if I'm in my software and I set my typography to 10 points in size, with 14 points of leading, which is a very classic, highly readable body copy proportion, I am locking into a mathematical matrix that relies on that specific 0.0138-inch granularity.
Yes, exactly. You are operating with the precision of a watchmaker. You know that 10 over 14 points will perfectly fill a specific depth of a page without a single fraction of a point left over. You aren't dragging a text box until it looks okay. You are engineering the space.
Engineering the space. I like that.
And this goes beyond just the vertical grid. It applies to the horizontal space between letters too. Kerning.
Right, kerning. Adjusting the space between two individual characters so they visually balance.
Exactly. When you kern professional typography, you are often making adjustments of half a point or less. We're talking about 0.17 of a millimeter. You are nudging a capital T closer to a lowercase o by the width of a single human hair, so the white space between them feels completely even.
That's intense.
An amateur uses a yardstick. They use large, clumsy measurements and let the software auto-space everything. A professional uses the scalpel of the point system. They understand that those microscopic adjustments are what make typography feel completely invisible and effortless to the reader.
That is a wild mental shift. It really reframes these archaic units from being annoying historical baggage to being a highly specialized surgical toolkit. Knowing that 1 inch is exactly 72.27 points isn't just trivia, it's the underlying code of the entire visual structure.
And it sets you up for the moment when that structure has to become a physical object.
Yes, and that is exactly where the narrative takes a very sharp, very dangerous turn. Because as beautiful and perfectly mathematically aligned as our Picas and points are on a brightly lit digital monitor, eventually you have to hit export.
The dreaded handoff.
Yeah, you have to send that file to a commercial print shop. And the moment that file leaves your computer and hits the print shop floor, the mathematical language we use to communicate changes entirely. We leave the clean, whole number world of points, and we enter the absolute crucible of physical production.
The transition from digital decimals to physical fractions. This is where most early career designers make their most expensive mistakes.
Let's pull the source material back up, because this second section of the conversion chart is arguably the most intimidating. We are looking at the direct translation from inch decimals to inch fractions. Now, in almost all design software, distances are displayed as decimals by default. If you drag a ruler guide out to create a margin, the software might tell you it's sitting at 0.125 inches.
Which is a nice, friendly number on the screen.
Right. And the chart lays out these base foundations, and they feel familiar. 0.125 is 1/8 of an inch. 0.250 is 1/4. 0.5 is exactly 1/2. 0.75 is 3/4. And 1.000 is 1 solid inch. I think anyone who has ever used a tape measure can visualize those.
Sure, the basics.
But then the chart takes a deep dive into the micro measurements. It breaks down the 16th and the 32nds of an inch.
The spaces between the spaces.
Exactly. And I want to read a few of these because the progression is dizzying when you see it laid out. 0.063 is 1/16. 0.094 is 3/32. 0.156 is 5/32. And then you get deep into the messy middle of the inch, where it states that 0.531 is exactly 17/32 of an inch.
Oh, man.
0.656 is 21/32, and 0.969 is an agonizingly close 31/32.
31/32. You are quite literally a paper's width away from a full inch.
I look at this chart, and I don't just see math, I see a translation dictionary. Because the designer is acting as the translator between two very different worlds. You have the digital software, which spits out clean decimals like 0.844, and then you have the physical print shop. And print shops aren't operated by mice and keyboards. They are operated by massive, terrifying pieces of industrial machinery.
Heavy metal. Guillotine paper cutters that slice through a ream of paper with thousands of pounds of hydraulic pressure.
Yes, steel die cutters stamping out cardboard shapes at lightning speed. And those physical machines, especially older or custom-built hardware, are often calibrated using fractional physical measurements. The operator setting up the machine isn't always punching in 0.844, they are dialing in a physical gauge to 27/32 of an inch.
Exactly.
But let me stop and play devil's advocate for a second, because I know what our listener is probably thinking.
Let's hear it.
We live in 2026. Everything is automated. I can send a digital PDF to a massive web-to-print automated facility halfway across the country. In a world of heavily automated digital printing, isn't memorizing that 0.344 is exactly 11/32 just busy work?
I hear this all the time.
Right. Like, why does a human being sitting at a MacBook need to intimately understand the relationship between 0.906 and 29/32? Doesn't the computer just handle the translation for us?
The computer will do exactly what you tell it to do, with absolute unthinking obedience. And that is exactly why it is so dangerous if you don't understand the fractions yourself.
Wait, really?
Yeah, because the computer doesn't know what paper is. It doesn't know how paper behaves when you fold it or cut it. It only knows the math you input.
Okay, so give me a scenario. How does not knowing that 0.344 is 11/32 blow up in my face?
It comes down to a principle we call error compounding. Let's step away from the abstract numbers and build a real physical object. Let's say you were designing a complex Z-fold brochure. It folds back and forth on itself like an accordion. To make a brochure fold properly, the inner panels have to be slightly narrower than the outer panels, otherwise the paper buckles when it closes.
Right, because the paper itself has physical thickness. It takes up space inside the fold.
Precisely. Now, let's say you calculate that the inner panel needs to be trimmed exactly at 25/32 of an inch from the edge to allow for perfect clearance. You look at your conversion chart, and it tells you that 25/32 perfectly translates to a decimal of 0.781 inches.
Okay, simple enough.
You type 0.781 into your software, set up your die line, and everything is fine.
That sounds like a success story. Where does it go wrong?
It goes wrong when the designer does not have the chart. Let's say you are rushing. You know the physical fold needs 25/32 of clearance, but you try to eyeball the decimal in the software. You look at 0.781 and you think, that's a really messy number. I like clean numbers. I'm just going to round that to 0.75 or maybe 0.8.
I mean, guilty. Early in my career, I absolutely did that. I would look at a number like 0.406, which the chart says is exactly 13/32, and I would just manually type in 0.4. I figured, what is 6/1000ths of an inch? It's literally invisible on my monitor.
It is invisible on your monitor. But physical paper and hydraulic steel blades do not care about your monitor's zoom level. When you round 0.406 down to 0.4, you have introduced a physical error into the blueprint. You just told the printer to cut the paper short by a fraction of a hair.
But again, it's just a hair. Does it really ruin the brochure?
On a single cut. Maybe you get away with it. But we are talking about a complex fold. That error compounds. Every time the brochure folds over itself, that missing 0.006 of an inch is magnified.
Oh man, of course it is.
The first fold is tight. The second fold starts to pull the paper diagonally. By the time you get to the final fold, the entire structure is warped. The text that you spent hours perfectly kerning and aligning to your pica grid on the front panel is now physically skewed halfway off the edge.
Oh, wow. So the decimal isn't just a coordinate on a screen. It's a set of physical instructions for a machine interacting with real-world material.
It is a physical blueprint. And if you, as the designer, don't fluently speak both decimals and fractions, you cannot communicate with the master printer on the floor. Imagine the printer calls you. They've run a test sheet and they say, hey, we've got a problem. Our die-cut machine is set to strike at exactly 21/32, but your digital artwork bleed is sitting at 0.6. It's misaligned.
If I don't know the conversions, I panic. I have absolutely no idea what they're talking about.
Exactly. But if you have this chart internalized or just sitting on your desk, you instantly realize the problem. 21/32 is exactly 0.656. Your artwork is at 0.6. You're off by over 0.05 of an inch. You can open your file, adjust the bleed to 0.656, and send it back before they run the 50,000 unit print job.
Which brings us back to the disastrous box at the beginning of the show. Fixing a mistake before it hits the press takes 5 minutes. Fixing a mistake after it's been printed, die-cut, and shipped.
It's not like hitting Command-Z on your keyboard. It is a total loss. Understanding this chart, treating these exact decimal to fraction conversions as non-negotiable laws of physics is what prevents catastrophic financial losses.
It's basically risk management.
100%. It cements your reputation as a professional. When you send a file that perfectly translates to the physical machinery, the print vendor trusts you. The client trusts you. You become known as a designer whose work actually functions in reality.
That is incredibly empowering. It takes you from being a decorator who just makes things look pretty and turns you into an industrial architect. But as we move further into this source material, you realize that physical production isn't just about where the blade slices the paper. Length and fractions only cover one dimension. When we design physical packaging, we are creating three-dimensional objects, and that means we have to grapple with the physical properties of the material itself.
Exactly. You are moving from a single line into two-dimensional surface area and finally into physical mass, weight.
And this brings us to the third major section of the conversion charts provided in our book. This is where we learn how to handle packaging design, paper specifications, and freight by using conversion formulas for area and weight.
And just like the fractions, the precision here is absolute.
Let's break down the area first. The source dictates that 1 square inch is equal to exactly 6.45 square centimeters. Going the other direction, 1 square centimeter is a tiny 0.16 of a square inch.
That's the micro level. Super useful for calculating small labels or foil stamps.
Right. But then it scales up dramatically. 1 square foot is equal to 0.09 of a square meter. 1 square meter, which is a massive physical space, is 10.8 square feet or 1.2 square yards. And conversely, 1 square yard is 0.8 of a square meter.
You're essentially mapping out the footprint of a billboard or a large-scale retail display there.
Exactly. And then the chart shifts into weight, which is fascinating to find in a graphic design reference manual. The book states that 1 pound is 0.45 kilograms. 1 kilogram is 2.2 pounds. 1 ounce is 28.4 grams, and 1 single gram is a microscopic 0.04 of an ounce.
The grams to ounces conversion is arguably the most critical metric for anyone dealing with paper.
And that is exactly where I'm going to challenge the premise again, because if I'm an early career designer, I look at these weight conversions, pounds to kilograms, ounces to grams, and I think, I am an artist. I am a visual communicator. I am not a warehouse manager or a shipping logistics coordinator.
Right, not my job.
Exactly. If my job is to choose the beautiful typography using our Picas and make sure the die cut fits using our fractions, why do I need to care about the weight? Why does it matter to me sitting at my laptop that 1 ounce of paper is exactly 28.4 grams?
If we connect this to the bigger picture of the industry, you have to accept a hard truth. Professional graphic design, especially packaging and editorial design, is logistics. They are completely inseparable. You cannot design a physical product without designing its physical impact on the world.
Okay, walk me through that. How does an ounce of paper dictate logistics?
Think about what you're actually doing when you specify a paper stock for a project. You aren't just picking a color or a texture off a swatch book. You're selecting a physical, dense substance. In the printing industry, paper is fundamentally categorized by its weight.
Okay, I've seen that, like the pound weight.
Right. In the US, it's often measured in pounds, like a 100-pound text stock for the inside of a magazine or an 80-pound cover stock for the outside. But internationally and universally in structural design, paper is measured in GSM, grams per square meter.
Ah, light bulb moment. Grams per square meter. That directly ties the weight conversions and the area conversions together into one metric.
Exactly. So when the chart gives you the conversion that 1 ounce is 28.4 grams and gives you the exact square meterage of a square yard, it is handing you the mathematical formula to understand the physical density of your design. The paper weight dictates absolutely everything about how the final object behaves.
Behaves in what way?
Structurally and tactilely. Let's go back to our ruined box scenario. Why did the paper crack when you folded it? Because the paper was too heavy, too dense, and you didn't account for the GSM. A 350 GSM paperboard, which is a very thick, heavy stock, has so much physical mass that if you try to fold it in half without mechanically scoring a hinge into it first, the tension will physically tear the paper fibers apart. The ink will just flake off.
Oh, that makes so much sense.
Conversely, if you design a box meant to hold a heavy glass bottle of perfume and you specify a 150 GSM paper, the box will completely collapse under the weight of the product.
So understanding the weight is the only way to ensure the product functions structurally.
Structurally, yes, but also emotionally. When a consumer picks up an Apple product box or a luxury watch carton, the immediate psychological feeling of expensive doesn't come from the graphic design, it comes from the mass, the density, the physical weight of the board in their hands. If you don't understand how to specify a high GSM board, you might accidentally design a luxury product that feels like a cheap box of cereal.
That makes total sense from a creative perspective, but you mentioned logistics earlier. How does this tie into the warehouse manager side of things?
So let me give you a scenario that happens all the time in direct mail marketing. You design a massive 100-page catalog for a major retailer. You decide to upgrade the paper from a 60-pound stock to an 80-pound stock because you want the photos to look richer.
Sure, better paper, better photos.
You think, it's just a slightly thicker paper, no big deal. But you didn't do the math. You didn't use the conversion charts to realize that 1 kilogram is 2.2 pounds, and you didn't calculate the total physical mass of the finished book. You just increased the weight of each individual catalog by, let's say, 15 grams.
15 grams? I mean, that is roughly the weight of 3 standard sheets of paper. It sounds like nothing.
It is nothing for one catalog. But your client is mailing out 500,000 catalogs across the country. Those 15 extra grams per unit multiplied by 500,000 units just added 7,500 kilograms of mass to the entire run. You have just pushed the entire shipment over the threshold into a much higher premium postal freight bracket.
Oh my God.
Exactly. Because you didn't calculate the weight, you didn't just change the feel of the catalog, you just blindsided your client with an extra $150,000 postage bill. They're going to care how nice your typography looks when they're explaining that budget overrun to the CEO.
That is terrifying. So knowing that 1 ounce is 28.4 grams isn't trivia. It is literal bottom line cost control.
It is absolute financial control. And the area formulas in the chart serve the exact same purpose for material costs. The source states that 1 square yard is 0.8 of a square meter, and 1 square meter is 10.8 square feet. Why does a graphic designer need to calculate square meterage? Because premium print finishes are priced by physical area.
Finishings like
Gold foil stamping, spot UV, gloss coating, soft touch laminations, even custom Pantone ink coverage. Printers don't charge a flat fee for those. They charge based on the square millimeter of material consumed. If your client wants the entire interior of a massive shipping carton flooded with a custom neon pink ink, the printer is going to use these exact area conversions to calculate the square meterage of the unfolded cardboard required.
That makes perfect sense. If I know the exact area of my flat design, I can accurately estimate the raw material consumption before we ever get a quote from the printer.
Yes, and more importantly, you can optimize it. We call it nesting, or calculating material yield. If you know that 1 square meter is 10.8 square feet, you can calculate exactly how many of your flat, unfolded box designs will fit onto a single standard master sheet of cardboard from the paper mill. You might realize that if you shrink the dimensions of your box by just 4%, you can fit 3 box templates onto a single square meter instead of 2.
Which instantly cuts the raw material cost by 1/3.
Exactly. And it dramatically reduces physical waste, making the entire production run more environmentally sustainable. The amateur designer just draws a box to look pretty and hands it off, crossing their fingers. The professional designer uses the area and weight conversion formulas to engineer a product that is cost-effective, logistically brilliant, and environmentally responsible.
It really is the difference between drawing a picture of a car and actually engineering an engine that can drive down the highway. Okay, so let's take stock of where we are. We have mastered the microscopic realm of typography with points and picas. We have survived the physical print shop floor by translating decimals to rigid physical fractions. We have engineered the physical mass, volume, and logistics of our packaging using area and weight. Mastering all of these constraints gives you immense power over the physical reality of your design.
But there's a catch.
Right. Because in today's industry, that power hits a hard ceiling if you only understand the physical constraints of your own home country.
That is the final hurdle. To truly scale your career, your mathematics must become bilingual. You have to go global.
And that brings us to the final and perhaps most vital section of our source material today, bridging the metric and imperial systems. Because let's face it, graphic design is a globally distributed supply chain. You might be designing in Los Angeles, getting client approval in London, and printing the physical object in Shenzhen.
It happens every day.
If you want to be a global designer, you have to intuitively understand both measurement systems to collaborate seamlessly without causing a catastrophe.
It is the ultimate test of a designer's fluency. Can you translate your intent across borders?
Let's look at the actual numbers the text provides to help us cross those borders. The source meticulously breaks down the direct metric to imperial equivalence. And it starts with what I consider to be the most foundational equation in all of global physical design, the Rosetta Stone. 1 inch is exactly 25.4 millimeters, or 2.54 centimeters.
Burn that number into your brain, 25.4. It is the bridge between two entire paradigms of thinking.
25.4, memorized. And the chart scales up from there. 1 foot is exactly 304.8 millimeters, or 30.5 centimeters. 1 yard is 914.4 millimeters, which translates to 0.9 of a meter. And going the other direction, 1 full meter equals 1.1 yards.
It is so close to a 1-to-1 ratio, but that tiny 0.1 difference becomes a massive liability at scale.
Right. The book also details the reverse micromeasurements. 1 centimeter is 0.03 of a foot, or 0.4 of an inch. 1 single millimeter is an incredibly tiny 0.0394 of an inch. And the source even provides a deep cross-reference table combining our previous terrifying section on fractions with the metric system. 1/16 of an inch is 1.586 millimeters. 1/2 of an inch is exactly 12.7 millimeters. And again, confirming the Rosetta Stone, 1 full inch is precisely 25.4 millimeters.
The precision the book insists on here is totally non-negotiable.
But let me challenge that non-negotiable precision. I look at this, and I agree you need a bilingual design brain, but I want to pose a real-world scenario. Let's say I am an American designer. I have a client who wants a promotional poster design, and they specify it needs to be exactly 1 foot wide by 2 feet tall.
Okay, standard dimensions.
Easy enough. But we are printing it overseas with a European vendor who requires all digital files to be set up in millimeters. I look at my chart and it says 1 foot is 304.8 millimeters. Is it really that dangerous from a practical standpoint to look at 304.8, say I hate decimal points, and just round it down to a clean 300 millimeters?
My point.
I mean, 4.8 millimeters is roughly the size of a pencil eraser. Does a pencil eraser's worth of physical space really matter that much on a poster?
This raises such an important point, and it echoes what we discussed earlier about error compounding, but on a much larger, global, and highly visible scale. You are asking if amputating 4.8 millimeters matters. In isolation? On a blank sheet of white paper? No, nobody would notice. But design does not exist in isolation. Visual design exists entirely in proportion.
Proportion. Walk me through that. What happens to the proportion when I drop that decimal?
Let's track your scenario all the way through to the end. You spend 2 weeks designing a stunning brand identity. You get the typography perfectly locked in using your Picas and points. You draw a circular geometric logo that is mathematically flawless. You place it on your 1 foot wide poster artboard. But you tell the European printer to output the file at 300 millimeters wide instead of the precise 304.8 millimeters.
Right.
By doing that, you have just arbitrarily shrunk the width of the canvas by about 1.5%.
Okay, at 1.5%. Again, that sounds incredibly minor.
It is minor. But did you also proactively shrink the vertical height of the poster by exactly 1.5% to compensate?
No, I only rounded the width down because 304.8 was messy. The height was 2 feet, which is 609.6 millimeters, so maybe I just rounded that to 610.
And right there, the design's dead. Because you altered the width and the height by different mathematical percentages, you have just warped the aspect ratio of the entire document. Every single element on that page is now mathematically stretched or squished.
Ouch, okay.
And while the human eye might struggle to immediately register a 1.5% distortion on a small 1 foot poster, a corporate brand identity relies on absolute, unquestionable visual consistency. And here is where the scale comes in. What happens when the client loves your 1 foot poster so much that they decide to use that exact same digital file as the template for a massive 30-foot outdoor billboard in Times Square?
Oh no, I see exactly where this is going.
Let's do the exact math using our conversion chart. 1 foot is 304.8 millimeters. 30 feet is 9,144 millimeters. If you use your arbitrarily rounded 300 millimeter file as the baseline proportion and the vendor scales it up 30 times, the width is now 9,000 millimeters. You are missing 144 millimeters.
144 millimeters. Wait, 25.4 millimeters to an inch? That is over 5.5 inches.
Exactly. You have amputated over 5.5 inches of physical space from the width of the billboard, while the height stretched disproportionately. Your perfectly balanced, carefully crafted geometric logo is now visibly horribly distorted. The brand manager pulls up to Times Square, looks up at a $50,000 media buy, and realizes their perfectly circular corporate logo looks like a squished egg.
And it all stems from the fact that I ignored the 0.8 on the end of 304.8 millimeters.
Yes. The cascading failure of rounding errors in global design is a very real, very expensive phenomenon. Understanding the precise math, knowing that 1 meter is exactly 1.1 yards, or that 1 single millimeter is precisely 0.0394 of an inch, is what allows you to fluently translate specifications across international borders without compromising the integrity of the design.
It's about maintaining the absolute truth of the file, regardless of where on earth it is being produced.
Precisely. Let's look at one more example from the chart that impacts physical manufacturing. 1 yard is exactly 914.4 millimeters. Let's say you are an American designer specifying the fabric for a massive wraparound banner at a global tech conference. In the US, you buy fabric and specify frame construction by the yard. You calculate you need a 10-yard long graphic. But the textile printing factory is in Asia, and they ask for the precise cut dimensions in millimeters. If you give them a rough estimate, say you just multiply 10 yards by 900 millimeters instead of the exact 914.4, the factory will dutifully cut and hem the fabric to your inaccurate numbers.
Because they only do what the file tells them to do.
Exactly. Fast forward 3 weeks. The fabric arrives in Berlin for the event. The installation team tries to stretch your printed fabric over a custom-built aluminum physical frame that was engineered precisely to the yard. But your fabric is short. It doesn't fit the frame. The installation crew pulls on it with all their weight trying to make it stretch, and the fabric tears right down the middle, 3 hours before the doors open to the public.
That is just brutal. It is genuinely incredible how these tiny fractions of numbers, these decimals that look so boring on a page, literally hold the entire physical world together. It makes you realize that being a global designer isn't just about understanding different cultural aesthetics or global trends. It is literally about speaking the mathematical language of the global supply chain. If you can confidently translate 25.4 millimeters to 1 inch intuitively, you become an indispensable asset to multinational agencies. You become the safety net. You become the person who ensures the files actually work everywhere, every time.
You transcend being just a decorator. You become an architect.
An architect. I really love that framing. So as we synthesize this massive journey we've been on today, this extremely deep dive into Chapter 1 of our source material, it is genuinely amazing to look back at the scale of what we've covered. We started in the absolute microscopic digital realm. We learned that the seemingly arbitrary math of 1 pica equaling 12 points and 1 inch equaling 72.27 points isn't arbitrary at all. It is a highly specialized base 12 system that gives you absolute surgical control over professional typography and unbreakable baseline grids.
And from that pristine digital typography, we moved onto the loud, dangerous floor of the physical print shop. We learned to act as a translator, turning clean digital decimals into rigid physical fractions. We saw how memorizing that 0.781 is exactly 25-30 seconds ensures the guillotine blade strikes true and prevents a microscopic rounding error from compounding and destroying a folding brochure.
From there, we expanded our view from mere length and cuts into the physical mass, volume, and area of packaging. We learned that graphic design is logistics. By understanding that 1 ounce of paper is 28.4 grams, we prevent catastrophic freight overages. By calculating that 1 square meter is 10.8 square feet, we optimize raw material yields, saving the client money and reducing environmental waste.
And finally, we scaled our vision to the entire globe. We bridged the metric and imperial systems. We saw how respecting the precision of the 25.4 millimeter inch and the 304.8 millimeter foot prevents massive aspect ratio warping and catastrophic installation failures on international manufacturing projects.
It is a profound realization when you step back and look at it. These numbers, these dense pages of decimal conversion charts, they are not just dry data tables. They are the invisible architectural blueprints of the entire graphic design profession. They are the specific tools that allow your imagination to safely, beautifully, and cost-effectively enter the physical world.
A designer who ignores these numbers is always guessing. A designer who masters these numbers has total, absolute control over their medium.
Absolutely. Now, if you are serious about taking control of your medium, if you want to be the architect whose files never fail on the press, you need this toolkit on your desk. I am dead serious. I cannot stress this enough. Grab your own copy of the Graphic Design Reference Plus Specification book. You can find it right now at the Amazon link https://amzn2/4bbob. Go down to the description of this deep dive right now, scan the QR code, and buy the book. Keeping this reference guide next to your keyboard will save you from making a $10,000 printing mistake, I promise you.
It really is an essential piece of gear.
And while you are down there scanning that code, please follow us. We are going to keep unpacking the invisible rules, the hard math, and the technical systems that govern great design, and you really need to be here for it.
It is simply the best investment you can make in your professional foundation.
So as you head back to your blank digital canvases, I want to leave you with a lingering thought today. A question to ponder the next time you are simply out in the world interacting with the physical products around you. Next time you hold a perfectly folded, beautifully weighted piece of product packaging, maybe you're unboxing a new phone or opening a luxury perfume carton stop, and feel the physical mass of the paper in your hands. Look closely at how perfectly the ink reaches the scored edge without spilling over. Analyze how seamlessly the lid slides over the base, and ask yourself, how many invisible fractional conversions, how many microscopic point adjustments, and how many perfect metric to imperial translations had to go perfectly, flawlessly right for this single beautiful object to exist in your hands?